Hey, welcome all. That's a familiar sound if you're used to the podcast and the live stream. That little tune of ours calling you to the common good here in the morning with our podcast and live stream. And it's a Friday, August 20th. Already well into August. I mean, you could call this pretty much in the bank. It's taken care of. And it's Friday, so that means we get to talk about science around here with Paul Wallace, astrophysicist, pastor, professor, and bird watcher. Hey, Paul. Good to see you today.
Thanks.
We are, I'm in Minneapolis. You are in Decatur,
Yep.
Georgia. I would love to know where you all are from, by the way. So let us know where you're listening from and watching from. And while we have our feet grounded on the floor in our offices and basements, our heads are going to go up into the space today because we're going to be talking about a journey through our solar system here with Paul Wallace. And we're going to talk about Uranus and Neptune, two of the little planets that, don't
We can even
get as
throw
much
in
attention.
Pluto while we're at it.
Oh, really? You want to do it? So we
If
just get all
things
three
get
of them?
slow,
Hey, now
if Uranus is not sufficiently fascinating, we can move on out to Pluto. too.
okay, so there it is. Question number one for our conversation is, of course, going to be what does the solar system and space have to do with us living here on Earth? So we'll get to that over the course of our conversation. But on this one, does one pronounce it Uranus or does one pronounce it as a giggling junior higher as Uranus?
Right? You can do either one. You're free to choose, and you'd be correct according to the dictionary either way.
Really?
So,
Well, it has been, junior, my favorite planet from names since junior high, of course, because it allows you to giggle.
Of course. And I have chosen to pronounce it Uranus because I'm a very simple person underneath the, everything else. And I cannot with a straight face stand up in front of 40 students and say Uranus over and over again in 100 different contexts and not crack up. So,
Yeah, because under that that candy coated shell of professionalism is a giggling little junior high.
It's
You keep
funny.
saying Uranus.
It's like those videos you see of the kid, and his dad pitching the ball to him, and the kid knocks it right back into his dad's crotch. Every time it's funny.
Yes.
Just never not funny. And
Basically,
so,
the reason there's YouTube and was America's funniest home
Exactly.
videos.
That's right.
Because
That's
just
right.
tickles us. All right. Well, let's start here. I mean, in some ways, we're just making sort of childhood jokes. But how do planets get their names? How did Uranus get its name? Do you know this?
I do actually. William Herschel discovered it. He was a British astronomer. He discovered it in 1781. He looked up in the sky and saw something that looked a little bit different than a star. It looked a little bit different color, a little bit fuzzy. Thought it was a comet, but watched it over time, and it moved through the sky against the stars slowly, just a few degrees per year.
Where was he when he saw this? Because I found that I thought Uranus was really hard to see up in the sky up there.
Oh, yeah. Well, actually, it is. But you can see it with your unaided eye. You can see it with your, but you got to know a few tricks to do it. You have to know exactly where it is. Yeah, it actually is. And so Uranus is in fact visible to the unaided eye, but you've got to have a really clear sky. You've got to know exactly where to look. And you have to have good vision, and you have to not look right at it.
That's awesome. A right place, clear sky, and don't look at it to see it. That is.
If you look directly at Uranus, it will disappear.
And would be quite an accomplishment without a mirror.
It would be.
Right.
Yes.
See, there it is. I just couldn't avoid making a Uranus joke. Hey, okay, so I was wondering if he was like in 1781, maybe the skies were generally clear in there. And I wonder if he was like in a high altitude and the air was thinner. Is that one of the ways he discovered it? Anything like that?
No, he saw it through a telescope.
Okay, through a telescope.
He saw it through a telescope and saw that it looked a little different than a star, looked a little bit fuzzy, and watched it over time. And it turns out that over the centuries preceding this discovery, people had put it down on star charts as a star and thought that people had seen it before, but had not realized it was a planet before. So people had actually seen the planet and recorded it as a star.
the stargazers of cultures 1,000 years ago, 2,000, 3,000 years ago. Is that still? Do we still have record of that? Do those records last, or how far back do the sort of stargazing
Not at that
patterns go?
level. We have some Babylonian records, Mesopotamian records from way long ago, hundreds and hundreds of years BC,
Mm-hmm.
even thousands of years BC, but not at this level. Not the level. The records that I'm talking about are probably since the 1400s, something like that.
Okay.
Not more
Okay.
recent than that. But there are observations of the sky and of comets and of eclipses and stuff like that
Yeah.
from thousands of years ago.
Is that all kept somewhere now? Like, has someone organized all the history?
Yeah, they have. I think there's a big the documents. I don't think there's one single place
Hmm.
where it's all located, but yeah, it's all been
Should be like
saved
a sky museum
and written
somewhere.
down, and it has been written down, has been recorded digitally.
Yeah. Yeah. Put together somewhere. All right. So how did it get its name? How did Uranus?
Yeah, so Herschel discovered it, and he was a subject of King George III, so he figured he'd name it George.
Really?
Yeah,
It's like, if I name this after the king, I think I'm gonna get on the king's upside.
So we've got Mercury, right? We've got Venus, we got Mars, Jupiter, Saturn, and George.
And George. So did he really first start referring to it as George?
Yeah. Well, George's star. I don't know how he fancied it up, but basically, it was George.
Okay.
And then French astronomers didn't really like that, and there was a sense that, at least among European astronomers, these names that had already been chosen, Jupiter, Saturn, were kind of, everybody agreed on that, and so there was some pressure. But it was decades after he discovered it that it was officially named. It was decades. I think early 19th century. It wasn't until it was officially named.
Okay.
And Uranus was the father of Saturn, so that's how that worked.
Yeah. So they again went back to this like mythology narrative, right?
Yeah.
And named after the gods of the sky. All right. How about Neptune, which we'll also talk about in a bit? Same thing with Neptune. They.
Oh no, the discovery of Neptune was crazy.
Well,
bonkers story.
Okay, this should have its own podcast, like a serial podcast.
Yeah. The discovery of Neptune is phenomenal. It's a phenomenal story. But I did want to mention something else before we leave the story of Uranus's name, to say that Uranus's moons are all named after Shakespeare characters.
Oh, come on. Seriously?
I'm not making that up. No, it's real.
I mean, it feels like people making a great discovery now and then, naming them after, a Lion Witch in the Wardrobe characters or something. Like what? Okay.
Yeah.
All right. So
anyway, Puck, there's Puck and Miranda, Oberon.
How about that?
Yeah. No kidding. Huh. So I just thought I'd throw that in there before we move on.
All right. So should we stay in the discovery narrative?
Yeah, I think so. Because basically what happened was they discovered Uranus in 1781, and they watched it over like 50 years. Mm-hmm. They watched it again because the planets move. The stars kind of stay fixed relative to each other, kind of like a backdrop. Okay. And the planets move relative to the stars. But the motion of Uranus was, it didn't match what Newton's law said it should be doing. By this point, Newton had dropped his big book and had made quite a splash in the world of science. And he was completely, everybody believed Newton was right.
Wow.
But the motion of Uranus did not accord with Newton's laws.
Okay.
Did not. And after 50 years, it was just not where it was supposed to be in the sky. And so what they did is they looked at the motion that Uranus actually displayed and said, okay, according to Newton's laws, there could be another planet out beyond Uranus, And if it's in this location, it could produce that motion of Uranus. So basically, the math told them where to look. Because of the motion of Uranus, they said, okay, let's assume there's a planet beyond Uranus. If that's the case, where should it be at this point? The math told them where to look, and they looked, and it was there. Just exactly where Newton's physics said it.
So you're saying when Uranus didn't comport with the laws of Newton, that was assuming that it wasn't a planet. So the Newton's laws led them to the conclusion that this is a planet and not something else?
No. What I mean to say is this. According to Newton's laws, okay, assuming Newton is right, Uranus should move in a certain way.
Okay.
Assuming there's no other planets out there, okay, Uranus should move in a certain way.
Got it.
But Uranus was not doing that.
So there was some other planet.
Okay, we believe Newton is right. So maybe there's another planet out beyond Uranus, tugging on Uranus, pulling it, slowing it down essentially in its orbit.
Okay.
It's the gravity that's the piece that I missed. I see that now. There's another planet beyond Uranus, dragging it, making it move more slowly around its orbit, dragging it back. And if that planet were to be out there, where should it be? Where should we find it? And Newton's laws said you should find it in this location in the sky. And they looked in that location of the sky, and there it was.
And that was Neptune.
Yeah,
I see. That's
so they discovered it.
I lost track of which planet we were talking about.
Yeah.
So they only discovered Neptune because of its influence on Uranus.
Right. And it was discovered mathematically before it was discovered like in the sky.
Are there any other planets that they think could do any other planets behave peculiarly in what we now know, where they think, there's some other force on them, or was that sort of the end of that story?
No, there has been some question that there could be a 10th planet out beyond, at this point, a 9th planet out beyond Neptune, bigger than Pluto and so forth. But the evidence is not conclusive.
Okay.
So
in that way, I guess Neptune and Uranus are really related planets in the story of their effect on each other and how they're related to each other.
Okay. And Neptune had been seen before by people with telescopes. Galileo saw it, and actually noticed that it looked as if it had moved a little bit. But he was following Jupiter through the sky, and so he kept on following Jupiter and left that little question mark behind. But it was Neptune that Galileo had seen. So it had been seen before, but not realized that it was a planet. So both Uranus and Neptune had been seen before they were realized they were planets.
And what year was that Neptune was discovered because of its influence on Uranus?
1830, 1850, something like that. Mid 1800s.
I mean, that's an incredible math that they're working out.
That's the thing. That's the thing. It's incredible what they were able to do.
And they're doing it on, they're doing it on parchment or paper or something.
Yeah.
They're not even using a fancy calculator, let alone what people would use now to run these kinds of calculations.
And also like certain kinds of like when Kepler was working back in the early 1700s, we have these things we call logarithms that are used. He basically invented, but he didn't have them. There's all these mathematical tools we have now. They didn't even have. They didn't use decimals either. They used fractions.
Oh my goodness!
I know.
And I'm flashing back to 8th grade and fractions class. Hey, I did see something about Herschel, the discoverer of Uranus, that he was a musician turned astronomer or whatever category they would have given somebody in the 1700s. Do you think there's something about that ability, that musical way of thinking about the world, like as a composer, that allowed people to do this math, to see these things?
There's math and music, and I haven't read the research, but apparently there is a connection, and it's basically the common thing between mathematics and music is the patterns, seeking out patterns,
Yeah.
regular sort of rhythms in natural world and mathematics and in music. Yeah, and if you actually just step back and look at a page of math and look at a page of music, I mean,
Yeah, there you go.
Both there's a lot going on. There's a lot of patterns involved.
Yeah, I mean that whole period of time from Bach through to Kepler and these people, like they created the very like Bach wasn't knocking off another version of music. He
Right.
created it, and Kepler isn't,
Right.
like you said, with the logarithms. He's
Yeah.
logarithms are. He's
Yeah.
generating them, like saying we need something
Right.
to accomplish this. I'll come up
Right.
with it. Man,
And
that
Newton did the
is
same thing with calculus. He needed mathematics to talk about the rates of change in the world around him, and so he invented it because he needed it.
See, this is one of the connections between the stars and the skies and the planets and life on this earth, is that everything we talk about is from the Earth's perspective. So it starts to give you insight into how the human being experiences the world. And
Yeah.
these folks must have seemed to just be out of their minds to other people who either didn't understand, weren't, into the sciences,
Yeah.
or
Yeah.
disagreed with them. I'm sure somewhere between, the 1781 discovery of Uranus and the 1830s or 50s of Neptune, there were all kinds of dissenters in there and arguments and people that were no longer friends because of the arguments they had.
Yeah.
Is that the case?
Yeah. Well, some of these guys, I mean, personality wise, like take Newton, for example. Boy, you would have not have wanted him at one of your parties. He would have just hidden in the closet, silently judging everybody. I mean, he was really thin-skinned, didn't really want to publish his work, was insanely touchy and competitive with other scientists. I mean, he was not fun to be around.
Wow.
But then there's other scientists, about the same time who you really would want to have at your party. Galileo would have been a smash at your party.
Huh.
Yeah. But yeah, there were definitely arguments. Newton hated this guy named Robert Hooke, and he just did everything he could to crush Hooke's career. Bitter guy. And Galileo had his own little petty, I don't know, envious. He was envious.
Yeah.
Some other
when they were first discovering these planets.
Yeah.
So at this time, so now there's 8 or 9 planets, depending on what you do with Pluto, right? What number of planet was Uranus and Neptune? Like what had they discovered?
Uranus would have been 7. By this point, there were 6. So Uranus would have been 7, and Neptune would have been 8. Yeah.
And what become? And then Pluto
was discovered in 1930.
Okay.
And so it was 9, and it only lasted for a few decades before it,
it's back up. So Neptune was the last one discovered. Is that because of its location, because of its size,
it's just so far away. It's so far away, and so it's dim for that reason, because it's just reflected sunlight that we're seeing.
Yeah.
So the further away it is, the less sunlight hits it. So it's not as intrinsically bright. And also it's further away, so it looks less dim. So it's just so dim. That's all there is. Also, it creeps around the sky so slowly that from night to night, you really can't see any changes in its location. You've got to go months or years before you really start to see a change in the position of these things. So they're small, they're dark, and they move slowly.
And it moves slowly in relationship to the Earth because it's so far away, or it moves slowly because it's small and has less gravitational effect on it?
Well, it moves. It's because there's less gravity. If you think about like the planets, like running around a track, Mercury's got the inside track, and then Venus has the next track, and then the Earth, and so forth. Well, it turns out that the outer planets not only have further to go around the track, but they're moving slower around the track. So
because they're smaller.
Because they're further away, and the force of gravity is so much weaker on them.
I see. So
the
it's
sun's
not
gravity is far.
Not their size that does that. Not their size that
No, it
causes
has
them.
nothing to do with their size.
Okay.
Nothing. If we put if we put Mercury out where Neptune is, it would move at the same
Okay.
rate.
Just so far.
All
Are
the
the planet
strength.
that's a great analogy about the track. We've all seen that before, or watched it on the Olympics. Those tracks are even. What's the spacing between all the planets in relationship to?
It really gets gosh, how can I say this? Let's see, the inner planets: Mercury, Venus, Earth, Mars, are all. Let me see how to say this. If you think of the Earth-Sun distance as a single unit, okay, Mars is at 1.5 units out.
Okay.
And all of those 4 planets are within 1.5 units of the Sun. Okay. Jupiter's at 5 units. Saturn's at 10 units.
Okay.
Uranus is at 20.
My gosh.
Neptune's at 30 and Pluto's at 40. So the outer planets the gaps between them are 20, 30 times larger than the gaps between the inner ones.
Got it.
Yeah.
Okay, so what do we know about the makeup of these things, and how do we know it? It was interesting to read, a couple little briefing articles on this that we're really guessing and working off of information from the late 1980s.
Yeah, but it's pretty good information. The composition piece is not very difficult. Relative, I mean, you can't just go up there and get a spoonful of it, and put it in your little analyzer. But determining the composition is actually one of the easiest things to do.
How so? What makes it easy to determine the?
Put it this way: if you take the light from the planet and put it through like a spectrum, a prism, to break it up into a rainbow, you can tell by that spectrum what the composition is.
So the sun rays are bouncing off of Uranus back here to Earth, and we can see what that spectrum looks like. And based on that, we're like, oh, this is a lot of methane or a lot of ice or a lot of something else.
Exactly. And we can get it down to a fraction of a percent. I mean, that is information that we really have know pretty securely.
So even though the light rays coming back are dim, there's enough information in that.
Yeah, but when Voyager went out there, it was so close to these planets. They had plenty. Voyager had plenty of light, plenty of light to work with. But yes, the answer is we can do it, even with that dim light. We can do it.
So what you're saying is, with the data we have on the light reflection, came from Voyager, which was the spacecraft from the 1980s that went shooting out there and flew by Uranus and Neptune.
Although, like I said, the technology we have now can easily get spectra of these planets from, like Hubble, for example, could easily get good spectra of these planets, even though they're so dim.
They can point the Hubble telescope at that thing and be like, "Oh, we know what's going on out there."
Yeah, that's right. And there's Uranus in all its glory. It looks like a cue ball, slightly blue.
I feel like I read something about Uranus that said Uranus changes a lot. Whatever the images are that Voyager took, or that we would know now, its atmosphere is really changing. Is that? Was that
Uranus? Or was that Neptune?
Well, you could be. If you call me on it,
I suspect, from what I know, that it's Neptune's, because Neptune's atmosphere does change. It's got a lot more sort of activity, storm-like stuff. You see right there. You know what they call that dark spot in the middle of Neptune right there?
What do they call that spot?
They call it the Great Dark Spot.
I felt there was a joke coming. That's great. So you're saying
that's what they call it.
Yeah, what we're looking at on the live stream feed is an image of Neptune, and you're saying there's a large dark spot, and they call that the large dark spot.
The Great Dark Spot, kind of like the Great Red spot on Jupiter, but it's the Great Dark Spot. Yep.
Is that great dark spot always there? Always in that spot?
As far as I know, it has persisted. As of at least 10 years ago, it was still there.
Hmm.
And so this image was taken in the 80s. So yeah, these long-standing storms, they do seem to persist.
So that dark spot.
It's a big storm. It's
A
like
big
a big
storm.
think of it like a hurricane or something
Wow.
on Earth.
It
Yeah.
just sits there. I mean, our hurricanes, I guess, because of our jet stream and atmosphere and everything, are moving all the time. That's the sort of the
Yeah.
point of them. This has hurricane winds moving,
Yeah. Winds
water,
are
floating
enormous.
water, and yet
Yeah.
it just stays right there on that one spot.
Yeah, part of the reason is that it's all like it's just like Jupiter. We talked about this with Saturn, I guess, a couple weeks ago. It's all gas. There's no land, right? You can't go walking around on Neptune.
Really?
Yeah, it's just
The
a big ball of
s-
gas.
and the scent again. I know. This was freaking me out about Saturn. There's not even a core in the center. Even that is just more compressed gas in the.
Yeah, probably with these outer planets, Neptune and Uranus, there might be a rocky core, but if they're so, it's not much. And the gas would be so dense that the transition between the gas and the solid would be pretty gradual. It wouldn't, you know what I'm saying?
Yeah, but okay, now that's got my head spinning. Gas can become more dense almost to the point of being a solid.
Yeah. There may be some liquid there somehow, but you can go
Okay.
from a gas straight to a solid. And so if you went straight down into that, the gas would get more and more and more and more dense, and there may be some liquid hydrogen down in there. Um, but by the time you hit the rocky core, if there is one, you would the pressure would be so
Meaningless.
high and so dense already that the transition would be a gradual one. I'll put it that way.
So, um, the gas puts out enough mass to have a gravitational pull to keep the storm and to keep the other gases
Yep.
inside of a circular shape. Because the
Yep.
thing that's still and this is the hang up that I've had since ninth grade is when you put water, we did this experiment in I think ninth 10th grade. You put water in a bucket, and if you just turn the bucket over, the water all pours out. But if
Yeah.
you spin that bucket really fast in your
Yeah.
arm, like wheel your arm over your shoulder and over your head, the water stays in the bucket.
Yep.
And I remember my science teacher saying, that's not what gravity is. That's like centrifugal force or centripetal force. I can't remember
Yeah.
which one. But like
Yeah.
that's a different thing. So the Earth doesn't stay. Stuff doesn't stay on the Earth because it's spinning fast. It stays on the Earth because of gravitational
Right. Gravity
pull.
is in this case. Gravity is like your arm spinning that thing around. Gravity is
Yeah,
pulling everything in the same way that your arm is pulling that bucket in all the time.
and that means there's something in the center of these, and that's what's giving them their round shape. There's something in the center that's so dense that's the force of gravity is pulling things toward that center.
Yeah. Yeah.
So I guess I assume that at the center of every planet, maybe every star, there was something so tight and dense in there that's the gravitational pull that was pulling everything else toward itself.
Got you.
And you're saying that's even a gas could even be that gas could be
Oh yeah,
so dense.
a gas can do that. Yeah.
I
But
guess
the centers
so.
of these
Again,
planets are the centers of these planets are not gas. They're either liquid or maybe there's a rocky core near the middle. But
because that's necessary at whatever point in the Big Bang that created these things.
it's just that's what happens when you take gas and compress it so much. You take gas and compress it, squeeze it, and eventually will become liquid.
And what
Eventually.
compressed all that
Gravity.
gas?
Gravity. The layers above, in a sense, pushing down on it. the layers of, you got the center of the core of the planet. Above that, there's all this mass pulling,
Yeah.
mutually attracting itself, pulling down into that central core right there.
So how do these planets get started? What's the
Well, we weren't there with video cameras, but we have a pretty good idea because there's several hints. One is you see these moons with all these craters all over them.
Mm-hmm.
And the Earth doesn't have many craters. It's got craters, but there's not so many. But then you look at the moon, you look at Mercury, you look at the moons of, Jupiter, Saturn, you look at Mars.
Right.
Just covered in craters, which is a clue that in the past, the solar system was a lot more violent place than it is now.
Things were colliding into each other.
Things were colliding. Yeah. It's believed that early in the solar system's life, it was just a bunch of chunks of gas chunks of rock and ice. It slowly built up over time into the planets that we have. And how that would happen is simple. If you remember that gravity is always on, you can't turn it off.
Yeah.
Once you get a sizable chunk that's bigger than average, it will attract other smaller chunks to it. And as it grows, it's like a positive feedback thing. The larger the thing gets, the more it sort of vacuums out the area around it. And so they just build. So we think that all of the planets were built by this accretion. It's called accretion. This accretion process, slowly building up out of smaller chunks of rock for the inner planets and of ice for the outer ones.
That's very helpful. And so all right. So be gentle with me if this sounds like a question that the answer is obvious.
I teach undergrads who don't know a thing about astronomy. I assure you, I've heard it before.
Right. There's nothing on our planet, on Earth, that is big enough, dense enough that it has its own gravitational effect. Is that right? Like all the things sitting on the table in front of me, all the things I'm making, nothing's like being pulled toward each other unless there's a magnet somewhere that's super close. So somehow gravity, okay. Do you see the question? Do you see
some things are big enough, like the Himalayas, for example, definitely affect local gravity. But no, the stuff in your room, yeah.
How do the Himalayas?
Gravity is not uniform around the world. In some places it's higher, some places it's lower, and the Himalayas just have a measurable effect on the local gravity field over there. For example.
Yeah. For example, like how? What's affected? What's
well,
affected
if you think about what gravity basically, think about it, it's a pull towards the center, what we call the center of mass of the Earth, which for us is just the center of the Earth. It's just a force that way. But if you've got, like a mountain here,
yep.
Like here's let me see, my mug is the mountain, right?
Okay. Yeah.
If you've got a little pendulum bob hanging down here, it would actually be deflected sort of toward the mountains. So without the mountains there, a pendulum might hang straight down. And this is simplified, but this is essentially how it works. You bring the mountains around and the pendulum bob would actually deflect a little bit.
Okay.
So it is directly measurable. Yeah.
I think I was in South Dakota where I went to one of these like freaky natural occurrence places, like a little built out tourist trap where like you stand on a board and you think you're going sideways and things are being pulled toward each other. You know what I'm talking about? These places, they have them around in North Carolina. Yeah, these places all over the country. Maybe people can put it in the chat or whatever. Where there's just forces of whether it's magnets in the ground or I don't know, it's hard for you to figure out. And kids go and they're like, yeah, you walk on this board and this funny thing happens.
Okay.
So well, if you don't know what it is, I don't know enough.
I can't remember enough about it. I totally believe you.
It makes me think, and then in spirituality, people would talk about this all the time, that there's certain places on the planet where the human body experiences forces differently. The Irish refer to their thin places in Ireland. So as someone goes around the planet, I mean, I guess when you go underwater and if you were to do, scuba diving, you would feel that, yeah, there's way more pressure
Yeah, from the
75 feet
water.
down than
Yeah.
there is here. And, something pretty basic like that. But on the surface of the earth, you're saying there's also places where whether we feel them or not,
Yeah,
the
we wouldn't
gravitational
experience them
pull.
ourselves. No, we wouldn't. We wouldn't feel it. We wouldn't be like fall over towards Mount Everest or anything. We wouldn't do
Yeah.
that. But a number of decimal places down, yeah, it shows up.
Wow.
But not
That's
where we
really,
would experience it. Now the stuff in your room there, like your pens and your hat,
yeah.
and your microphones, those definitely have gravitational fields, but they're just so many decimal places down in the force that we just don't experience them. But if you took your hat and your microphone and put them out in space, and just
Yeah.
let them go, they would drift towards each other, and eventually, and
Really?
it wouldn't take that long. I mean, if they put them a few meters apart, I don't know, maybe take a few days, maybe a week or two before they hit each other.
Okay, so
But
two
yeah,
questions in the chat. David Abram King says, aren't the centers of some of these planets like plasma? That's an interesting question.
they're not plasma. They would just be really, really dense rock or liquid,
Okay,
but
so
not
they're
plasma.
not plasma.
They're not hot
Plasma.
enough. They're not hot enough to ionize atoms, which
Got it.
is what you'd have to do to get a plasma.
Yeah, which is pretty cool. We had to have part of our fireplace cut out to put a gas fireplace in, and it was
Yep.
welded in. They had to come in with a plasma cutter, which is like a blowtorch that changes it ionizes the atoms and changes them around so they can take it out. Like it doesn't just cut it; it changes them. And do you know about I'm a nerd on plasma for a minute. Do you know about these plasma incinerators for dealing
No, but
with
it sounds like
garbage?
fun.
It's the future of it all. What's going to solve our trash garbage problem on the earth is plasma incinerators. They don't burn because that's a different process when you
Mm-hmm.
burn something.
They just
Plasma
they just disassemble them basically.
disassembles them at the atomic level and it just
Yeah,
goes away. And so there's these a dozen or so around the world, and they're very expensive, but they're coming down in price, and they're going to be the thing that's going to deal with all the stuff that we
and
end
they
up
can
with. It's
build them
just
on this and operate them on the scale that would be required.
yeah, yeah. They
Wow.
operate them. They operate them around. They're big closed systems where all the energy is being kept in it and running itself. It's
Wow.
incredible. Look up plasma incinerators. Incinerator makes you think the wrong word, but
Right,
it's
right. It
not.
makes
It's
you
not
think
like burning.
fire, but it's
Yeah.
not.
Okay. And then Perry Knight says we should have talked about how mountains pull on satellites as they go
Yeah, I'm
over.
sure that
So
they must have an effect. Yeah, because like I said, the gravitational field, like say above the Himalaya, would be stronger than it would be above, say, the Pacific Ocean.
hmm.
So yeah, I'm sure that has an effect on the
Would that be
orbits of
true on
satellites
on
over time.
airplanes too? Yeah.
No, I don't think so because I mean satellites go over. They have nothing to support them. They're just orbiting,
Oh,
right?
I
There's
see.
nothing, and they do it over and over and over again. So you get the cumulative effect that you wouldn't get with an airplane.
Okay.
They pass overhead every 90 minutes or whatever. So you know, little bitty differences would add up in that
Yeah.
case.
So Catherine Ayers says she's found that some sort of feeling when she's in the redwoods. Maybe she's redwoods in California, redwoods area. These big, massive trees that maybe when you walk through there, is there enough sort of gravitational pull on
No,
any
I
of
don't think
that?
it's gravitational. I definitely think there's something happening there,
Yeah.
but I would not point to any fundamental force of the universe of
Okay.
the four that we deal with every day as physicists.
Which
But
are, will you remind us of the four?
sure there's the big G, gravity, and
Uh-huh.
there's the basically electromagnetic force,
Yeah.
and those are the only two forces that you and I have ever experienced on any conscious level. So
Okay.
friction, baseballs being hit by baseball bats, the force holding the cup up on my desk here, all that, everything that's not gravity, every force you've ever experienced or know about that's not gravity
Yeah.
is electromagnetic. And the other two only operate at very small distances on very small scales. There's the strong nuclear force, which keeps nuclei. Think about this for a moment, Doug. Think about this for a moment, everybody. A carbon nucleus has 6 protons in it and 6 neutrons in it.
Okay.
But those protons are all like super close to each other, super duper close. But protons don't want to be close to each other because they're positively charged, and like charges repel. We've all learned that in 4th grade or whatever. So those protons, there's a lot of repulsion. They're trying to get away from each other. So there's got to be a stronger force keeping them together.
Yeah.
Right? And that's the strong nuclear force.
And do we call do professionals in the field call it that because
that's it. Strong
they don't really
force.
know what's going on? Like is it possible that that's part of a whole other force field?
No. Yeah, it is. I mean, we've dug down into it, and we have some ways of modeling it and thinking about it in terms of things called gluons. How's that for a particle name?
Gluons, yeah. That they're gluons are another particle. Is that right?
They're what is a kind of particle we call boson. It carries a force.
The force particle.
Yeah.
That's cool.
Like a photon. But professional physicists call it the strong nuclear force. That's what it's called, and it's strong relative to the weak one.
Yeah. So it's SNF and then WNF, strong nuclear force, and then the fourth is weak nuclear force. Are those the 4?
No, yeah. So strong and weak nuclear forces, gravity, and electromagnetism. Those are the 4.
Huh.
And so when I say that, the whatever the sort of the emotional, spiritual thing that you experience in nature, whether it's in the redwoods or Alaska or out at the ocean, whatever, would not. I mean, that's a question that the physicists would just say we don't do that. But there is certainly something going on in the mind there that could have its source in one of these forces, but it's certainly not a gravitational thing.
Yeah, some of the spiritual, or more fully human enterprise people that I pay attention to talk about consciousness as if it's perhaps one of these like forces. Like consciousness itself might have an effect on human beings and animals and other living creatures that has something. Maybe it's less like gravity or even electromagnetism, and more like these strong and weak nuclear forces, that there's something in all that. Really, I just find that fascinating. Okay, so what else? What I sort of took you down a road to explain, what's going on this planet. But what else? What else is there about Uranus and Neptune are particular and unique that we should be?
They both have rings. All the big outer planets, Jupiter, Saturn, Uranus, and Neptune, all have rings.
Is that because they're out there further? What makes them ring capable and we don't get rings here in the U.S.?
Well, Mars may have a ring in a few tens of millions of years because one of its satellites is falling in.
Okay.
And will eventually be broken up by Mars's gravitational field and could actually become a ring. But is
there no one in the universe that wants to put a ring on the Earth? No one wants to put a ring on it.
I think that'd be awesome to have a ring.
Yeah, we're never going to get a ring. We're never going to get a ring in the Earth. The Earth's never going to have a ring pattern.
Nope. That'd be awesome if we did, but I think the outer planets have them largely because I think their source is satellites that spiraled in and got broken up into thousands of pieces by their gravity. But for a couple of reasons. One is that the gravity is a lot stronger than the Earth's because they're so much more massive than the Earth.
Okay.
But also they have more satellites. Like Jupiter's got 80 something, right? Neptune has at least 14 that we know of. Uranus has maybe 40 that we know of. I can't remember the numbers.
These are
There's a lot.
moons, what we would basically call a
Yeah,
moon, or is
yeah,
this? Yeah.
yeah, moons. And so these moons are, more likely to, be crushed by the gravity. There's more moons out there to become rings.
Okay.
So,
Oh, interesting.
so
So if we broke up our own moon, boy, that'd be just to get a ring out of it. That'd be no good.
boy, that would be a hell of a ring too. Our
Yeah.
moon is really something. Yeah. Our
Huh.
moon's a little weird, by the way. I should say that relative to the size of Earth, it's really weird to have a moon that's so big. And it's certainly
Yeah.
unique. It's certainly unique in the solar system.
And
But what we,
seemingly moves around the sky in a way that I just cannot figure out. Like some parts of the, you go out and look at and the moon's, cross the street, and 3 hours later, the thing's behind my house over my head. Like that thing is moving
yeah,
around.
it's
What
tricky.
is it? What is it doing? Maybe people understand moon patterns, but I'm just like, I mean, I guess the like how, if it's a full moon or a half moon or a quarter moon or a sliver moon, I get
Yeah,
that.
it's
Why
it's
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 where it is at any given point is like, I don't know what that thing is doing. It's just
it's really
bouncing
pretty
around.
regular. If you were to watch it regularly, you would it wouldn't take you more than a cycle or two before you had it figured out. If you were to watch it nightly, like record it and think
Really?
about it every night, yeah, it's a definite pattern for
Okay.
sure.
So it's
You'll
not
never
as
you'll
random as
never
it
see
appears to me.
no, you'll never see it in the north, for example,
Yeah, why is that? Do people in
because
Australia on the bottom of the earth do they see it in the
they
north or
see it, but we see it in our southern sky. They see it in their northern sky.
in the northern sky? Yeah.
Yeah.
Yeah. So it's that one person from Australia that's listening to this is like, "What? It's always in the north."
Yeah, right. I'm very, very
Yeah.
northern hemisphere
Yeah.
centric.
Yeah, that's right. Yeah, okay, so it's always
For us,
okay.
it's always it's in the southern sky pretty much always.
We'll do a whole moon thing some other time. All
That's
right.
what we
So
should
anything
do.
else? So Neptune and Uranus, they have
Okay.
they have
Rings.
rings. They're
Yep, yep,
gaseous.
yep. They have
Uh,
rings. Uranus. If you look at this is one nice thing about Uranus that not many people know. You can't tell it looking at this picture. It actually has the second most elaborate ring system after Saturn. Um,
really?
and there's some good pictures of it where they look at it in infrared and or UV where you can see the
Hmm.
rings nicely.
How does
But
it compare in size to the Earth?
about you can put about 4 Earths across it.
Wow.
So the diameter is
I
four
mean,
times that of the
I
Earth.
guess yeah, because it's far away. I know. I guess I was just thinking it's small, but that's just a
Yeah,
perception
and
problem.
you have
Just
no
because it's
and you have no sense of scale with a picture like
yeah,
that. I mean, that could literally be a ball. I mean, you have no sense of how big it is. But
yeah,
no, it's about 4 times the Earth's diameter.
four
So
times
it's
the Earth.
pretty
Yeah,
big,
it's
and
big.
that's roughly the size of Neptune as well.
Okay,
They're,
they're
they're
both
about the
big.
same. Yeah, both big, about the
Yeah,
same size, but not as big as Saturn or Jupiter. But
and
go on.
other than Pluto, is
Yeah.
Earth the smallest? What are the sizes generally? Just
Mercury is the smallest. So if you don't count
oh,
Pluto, Mercury is the smallest, and then Mars, and then
really?
Venus, and then Earth. So Earth is the largest, not by much. We're just slightly bigger than Venus,
Oh, oh,
just by a few percent. So
that's
Earth and
yeah,
Venus are really about the same size, but
that's interesting.
Mars is about let's say about half the diameter of Earth, something like that. Um, and Mercury is maybe fourth to a fifth. No, I would say Mercury is probably about 40%
Hmm.
the diameter. And I think Mars is bigger than half. I think Mars is maybe 60%. I have to look it. I can't remember.
Yeah, but that's helpful.
Yeah, that's
All
definitely
right.
the order.
So a few minutes ago, David
There you go.
Abram, what is that? Oh,
That's
it's yeah,
Uranus.
and Uranus like rotates on its side. Is that
Yeah,
another
that's
thing
what that's
that's
what I was getting at. Yeah, all
okay?
the Earth has a 23-degree tilt, right? All our little globes everywhere have this nice little tilt. 23 degree, 23 and a half. Uranus is like 98 degrees, tilts 98 degrees. So it basically is on its side.
Okay, so the Earth got its tilt, its 23-degree tilt, because it got hit by something and
Yeah,
that
it got whacked by
knocked it,
something. Yeah,
and it,
yeah.
it just can't seem to get back up. Just can't
No, and
seem
it
to.
won't. I mean, it changes over time. There's a little thing called nutation. That tilt varies slowly. I don't remember what the cycle is. Maybe a couple 100,000 years or something.
Okay, so nothing we have to
It
worry about,
changes a little
and
bit.
that's what
Just a
accounts
little.
for our seasons. Is that
That's
right?
right. That's
That's
right.
that.
That's right.
So if yeah, um,
So the
so
seasons on Uranus are wacko.
okay.
That's the official scientific term for it.
So it is. So I'm picturing this now. Like I think about the Earth, and it's spinning on its 23-degree axis, but it's
Yep,
spinning, and then it's also moving around the sun.
that's right. Maintaining
So
that 23-degree tilt.
so for Uranus, it's spinning and also moving around the sun, almost like it's a little wheel. That's is it
Yeah,
spinning the same direction that it's moving? I mean, I know there's
yeah.
no friction up there; it's not being pulled along, but
So no, it's spinning. So it's basically, think of this: sometimes, and put it this way, sometimes the north pole of Uranus points right at the sun,
okay. Oh,
and
sometimes.
then half an orbit later, the south pole points right at the sun. Okay, it maintains.
I'm trying to spin in my chair to get that. Yeah, that I got it.
So basically, if this is Uranus here, the north. So here's the sun.
Yeah, of course.
Uranus right here, North Pole. As it orbits, the North Pole maintains its orientation.
Yeah, look at
It
that.
points away
Right.
from the sun and then comes back around, and then another half cycle later, the North Pole points back at the sun.
Huh.
So the
That's
seasons on Uranus are crazy.
wacko. Wacko, I should say. Yeah.
Wacko.
All right. Anything else about either of those? Because there's two other questions about the moons that people have that I think we should get to.
Okay,
Just to
yeah. Real quick,
please
the blue
people.
color, the slight blue color you see on Uranus, and the deeper blue color, that's not a visible light picture. If we saw Uranus with our own eyes, it wouldn't look like that. That's infrared and or UV. I think
Oh,
it's UV actually. So that's not how we would see it. That boring cue ball picture, that's what we would see.
I
And you can
see.
see that it's very slightly blue. And you can
And what
also see
what gives it
that
that blue
yeah,
hue?
methane, which is stinky. Uh, for us, it's stinky.
So
It's and then
Dan warned us about this coming in that Uranus also lets off methane and is stinky like a
it
fart.
sure
So
does.
just
Yep,
again,
yep.
it's the
There it
junior
is.
hire's favorite stinky Uranus planet.
And Neptune has more methane, and so it looks more blue. It's the methane that gives it that blue color.
Earth is not seen as blue because of methane. It's because of the water or the
Uh,
sky, the atmosphere.
yes, it's because of the atmosphere. Because
Atmosphere.
yeah, the atmosphere said to it scatters blue light. In other words,
Yeah,
if you take a bit of atmosphere and shine white light through it, the red will pass right through the atmosphere, but the blue will bounce around a lot,
got it.
and so it looks blue because of the atmosphere.
Yeah, and that's just helpful for people to know that, like the blue water of the, in the Caribbean, it's not blue water. It's
No, it's all
reflecting
sky.
the sky, and the sky is just holding in the blue light waves because our atmosphere doesn't let it out.
That's right.
It's kind of
Exactly.
cool. And but we always refer to Earth as the big blue planet. We're the blue one, and then there's two others that are
Yeah, and there's a bigger, bluer planet. Yeah, which is Neptune.
yeah, yeah. Huh. Well, classic Earthlings, just sort of
Yep,
bragging
yep.
about
That's right.
our Earth-centric
That's right.
opinion about this. All right, so first of all, Brooke is saying please do a moon video. So we will moon you sometime here on the Common Good podcast, and we'll do a moon video. Jim asks a good question. Does the moon rotate like the Earth? And I think I know the answer to this one, but you should probably answer it because I'm likely to be wrong.
It does rotate, but it keeps the same face toward us all the time. It's
What you talking about, Willis? That reference from Different Strokes.
yeah. Oh yeah. Gosh, I know it. Yeah. So
It rotates, but keeps its same face toward the Earth all the time. This sounds like one of those riddles that you're supposed to
all right.
solve.
I could draw a picture of this. It's hard to do with my hand. I need to have a little. I need to be in front of a classroom here, but
Okay.
Yeah. So here's the thing. So here's the Earth.
Okay. Okay. He's
Let's
got
say
a
that we
fist up.
let's say here's the moon.
Okay. And the moon's a
And
finger
say that
pointing at the
and
fist.
say that we go to the moon and we plant a flag pointing straight up towards the Earth.
Okay.
Okay. So my
Yep.
finger's the flag.
Yep.
Okay. A
As we
quarter of an
did, right?
orbit.
We went to the moon and planted a flag there, so people can
Yeah.
imagine
Yeah.
that there's a
Yeah.
flag
So
pointing
imagine the
at Earth.
flag is pointing straight towards the Earth.
Yep.
Now, a quarter of an orbit later, the moon's up here, right? But now the flag points down.
I don't think we ever know where the moon is. I think it just bounces around like a billiard ball unpredictably. Well, let's say
so,
you're right. Okay.
so as it orbits from here to there, the flag maintains its orientation towards the Earth.
Okay.
The moon has gone through one quarter of a turn. Not
Okay.
only has it gone one quarter of the way around the Earth, but down here the moon points to the right. I mean, the flag points to the right, and up here the flag
I
points down.
see.
Right.
Wow.
So
Wow.
the
This is spatial.
so
Yeah.
the moon has gone through one quarter of a turn between here and there, and that
I see.
flag maintains its orientation the whole time around. So the moon rotates once for every time it orbits the Earth.
So the
Once.
Earth is spinning, let's say, left to right in an
Yeah.
orientation.
I can't
And
do
then
that with my wrist, really.
so if it's spinning left to right, then the moon is spinning sort of top to bottom,
Yeah.
rotating top to bottom.
Yeah. No, in this case, the Earth would be rotating like around my
Yeah.
wrist this way.
Yes.
Yeah.
And
Yeah.
the moon is rotating like a
It's
wheel
yeah, in the same direction.
in the same direction.
It's all counterclockwise seen from.
So we never see the back side of the moon, or
We never
as
see it.
Pink Floyd puts it, the dark
There's not
side
a
of the
dark
moon.
side. There's not a dark side, but there is a far side that we can never see from the Earth. We always see if you go and look at the moon, you'll see the same sort of patterns on it every time it's full. It looks exactly the same. And
Well,
you can
that's
see the same stuff there, no matter if it's half or whatever. It's the same face is always pointed towards us.
And the flat earthers have a reason for this, because that's all kind of hologram stuff. That's why it's flat dimensional. I don't know if
They
you
got
know
reasons
that,
for everything.
The Chinese recently shot a satellite to the moon, or a lander on the moon, and shot it to the back side of the moon and landed back there. I think we talked about this like 2 years ago or a year ago or
Yeah.
something.
Yeah, a year or so ago.
Anything that has it come from that, or are they?
No, I haven't kept up with that. I don't
Yeah.
know, but that was quite a nice little accomplishment to land it back there.
Yeah.
Because you can't get the radio signals are tougher.
Yeah.
Because they don't. You have to go through the signals have to go through the moon. So
Yeah, they
it's
should
tougher.
figure out a way to like put a satellite way out there that's a mirror to bounce it off the satellite from the backside of the moon, off the satellite, back down to Earth.
I can't remember how they set that communication up.
They did something fancy
But
pants.
we definitely got we have their satellites. We definitely have put satellites around the moon, and we got really nice maps of the far side of the moon long before they landed there.
Oh, is that right? And it's essentially the same. No. The sun shines over there too, right? We just don't
same
see
amount.
it.
The far side gets the same amount as the near side. We just don't see it.
It's just as lit. So this idea that it's the dark side of the moon, that's again just a perspectival statement. Wow, boy, I like science class on Fridays.
Yay!
Hey, thank you to everybody, Marty and David and Brooke and Jim and Perry and Melton, who misses the Redwoods. Hope you find him again. And Catherine, Rick, and I know Rick put in the chat, I didn't vote, and then a series of emojis. So maybe just more commentary on where this is playing than the words that are playing, but we appreciate anybody that's willing to chat on the chat, and we appreciate everybody who watches and who sends us little notes on the podcast as well. So you can send us notes if you want to at podcast@votecommongood.com. And we'd love to know about how you appreciate the podcast. Paul, thank you, and enjoy the weekend. Are you a bird watcher hunting this weekend? Do you have?
I might go tomorrow if it's been really humid and rainy here.
Mm-hmm.
We got some of the remnants from that tropical storm earlier in the week.
Wow.
And the humidity is just unbelievable, and it's still getting up into the high 80s, low 90s every day.
Yeah.
And it's not a good time for birding this time of year. It's about to be great, though. We're out on the edge of fall migration. So,
Okay. Well, we're doing this bike trip across the country, San Diego to St. Augustine, Florida, to tell the story of the border. And one of the towns that we were in is like a chief birding area, Patagonia, Arizona.
oh
And
yeah,
people
man,
go there.
they got it good over there. They get the migrants coming up from Mexico.
Yeah, the bird migrants.
Yeah. Yeah, right.
Yeah, you should.
I need to specify.
You should come and join us about that down there along this way. And anybody should come and join us anywhere along the route that you want to. WeThePeopleRide.org. You can find out all you need to know about that. All right, Paul, thank you. And we'll see you in a couple weeks.
All right. See you.
All right. See you, everybody.